We want to enable real-world quadruped robots to be able to expand their library of locomotion gaits in an iterative manner. In our method, we construct a library of independent policies and develop a meta-controller that enables the transition between policies. In our policy library, the complexity of each locomotion gait is contained by training independent reinforcement learning policies that each specialize in a different gait. We adopt 3 gaits representative of our robot's capabilities: pace, trot, and stand. These allows us to perform transitions of type static to dynamic, dynamic to dynamic, and dynamic to static. Through the use of domain randomization techniques, we develop robust policies that can be deployed with an A1 quadruped robot and work in a variety of environments. With a library of robust but independent policies, we need to introduce a mechanism that links the policies and enables the transition between any pair in the library. We construct a dataset by executing transitions with a random strategy between every policy pair available in the library. Then, we learn a mapping between the latent representations of the current running policy and the success of a transition. This function is modeled by a neural network and is called the transition net. At deployment time, we employ a meta-controller to execute transitions between the policies in the library. We start with an active policy which continuously sends the joint commands to the real robot. At some point in time, a different policy from the library is queued, and the meta-controller starts querying the transition net at every step. Once the score of the transition crosses a certain threshold, the running policy is immediately switched for the queued policy. The new active policy now takes control of the robot and the transition is complete. Our meta-controller paired with the transition net enables the transition between the policies available in the library in a variety of environments in the real world. We successfully deployed our method in indoor office environments and with carpeted surfaces, as well as outdoor environments with more challenging terrain such as grass, mud and gravel.